In control theory, the Bode plot is a very important tool to analyze the stability of the circuits. We usually use the Bode plot to describe the system transfer functions, amplitude, and phase features. So using Bode plot can help us to read the frequency features of the system very conveniently. So in this section, we are going to learn about how to plot the Bode plot. So first, let's have an overview of the transfer function. Transfer function is a mathematical tool which reflects the relationship between the input and output. Suppose we have a system. We can use a block and a system transfer function GS to represent the system. So here is the input, XS. Here is the output, YS. So for this block diagram, we can see that the GS equals to the ratio between the output YS and the input XS. So S usually refers to the frequency domain. And in order to analyze the phase and magnitude features for the transfer function, we can substitute S by J omega. So if we substitute S by J omega, we will obtain the transfer function as J omega. And we can calculate. So this would be a complex number, right? Complex number means that we can plot this complex number in the complex plane. So for example, here is the real part, origin, imaginary part. So given a complex number J omega, we can have two dimensions to measure the J omega. One is the magnitude, right? The length of the complex number. And the second one is the phase. So we can write the mathematical expression to calculate the magnitude and the phase. For example, the magnitude would be equals to like the length of this complex number, right? So it should be equals to the square root of the real part square plus imaginary part square. It's like we look at this triangle, right? Triangle. So here is the real part, here is the imaginary part. So the length here is equals to the square root of the sum of the real part square plus imaginary part square. And for this angle, right, we call this as phase. So we use this symbol to denote the phase angle. So as we can see here, this angle will be equals to the arc tangent, right, of the imaginary divided by the real. So that's the way how to calculate those two quantities. Okay. So next, let's look at the Bode plot. So in Bode plot, namely we use plots to represent those two quantities, right? So for example, we can plot the magnitude plot. For magnitude plot, so it's typically expressed in decibels. So it's like we use a plane. The x-axis is the frequency, right? But we use log scale. And for the y-axis, it is the magnitude. So we use decibel to denote the magnitude. So this usually we would use like G in decibel magnitude equals to 20 log. The base is equals to 10 of this absolute value of this magnitude, right? So here we would have 20 log G. So this is the way we plot the magnitude plot. And of course, the frequency, right? Frequency axis usually expressed in log scale. So you might be curious about why we use log scale, because it will bring us many convenience to simply plot the standard transfer functions Bode plots. I will explain later on. Okay. And next, let's look at what general rules do we have to help us to plot the Bode plot of a complex system. So general rules. So first rule is about the magnitude plot. For magnitude plot, if we have a pole, right? Pole means that the denominator of the transfer function equals to 0. So if we have pole, then we would have the slope of magnitude plot. Changes by minus 20 dB per decade. So this means that for each decade frequency change, we would experience a drop of the magnitude by 20 dB. Okay. At every pole frequency. And for the zeros, right? Pole means that the denominator equals to 0, right? So 0 means the numerator equals to 0. So for zeros, we would have a similar rule, but different sign here. So if we have zeros, we will have the slope of magnitude plot changes by plus 20 dB per decade at every 0 frequency. By the way, those are kind of approximation, right? If you want to get the accurate plot, of course, you can input the transfer function into MATLAB to help you to get the accurate plot. But those kind of approximation is considered to be roughly accurate, okay? And the second general rule is for the phase plot. Phase plot is like we also have two conditions. One is for pole, one is for 0. So if we have a pole whose frequency is omega m, then the Bode plot will begin to fall at 1/10 of this pole frequency, 0.1 omega m. And the change will accumulate to, so changes to minus 45 degree at omega m. And eventually approaches minus 90 degree at 10 omega m. So this means that the change only appears within 0.1 omega m and 10 omega m. Beyond the 10 omega m, the phase plot will be flat. Right? Total change is minus 90 degree. And similarly for 0, we also have the similar rule, like 0. If we have a 0 whose frequency is omega m, then the phase plot will begin to rise at 0.1 omega m and changes to plus 45 degree at omega m and eventually accumulate positive 90 degree. So approach at 10 omega m. Similarly, beyond. So similar to the pole, so the net change will be only 90 degree. So beyond this 10 omega m frequency, there is no change. So it's going to be flat. So that's the phase plot. Third one is the what if we have multiple poles and multiple zeros? How to obtain the Bode plot for the entire system? So for complex system, we can do like this. We plot the Bode plot of both of each pole individual pole or zero. So suppose a system can have many poles and zeros. We can plot each individual poles and zeros Bode plot and add them together. So we can get the Bode plot. Of the entire system. Okay, so in this section we have introduced the basic rules to plot the Bode plot. For a complex system, we can first decompose the complex transfer function into the components of different individual poles and zeros. And we plot each individual's pole and zeros Bode plot and add them together. So we can get the Bode plot of the entire system.